Hey there, physics aficionados. This is Mr. Hutchison, and I was just going to show you how to do a couple of things in your packet that you're working on right now. So let's go ahead and open this bad boy up. We're already past the very first beginning stuff. We did exercise 6. You can see that picture on Edmodo. We're on into 5.2, conservation momentum. This is actually going with chapter 8 in your updated textbook now. And then you're gonna get some more solved examples there, example 5, 6, 7, and then you're gonna get into exercises 7 through 11 through 12, 13, 14 that you're going to need to do. And then on into additional exercises that are a mixed grab bag of everything you've been working on throughout the whole packet. Now I wanted to do one of these with you to show you how to do conservation of momentum and to give you a freebie on these. Now, when do you use conservation of momentum? I'm glad you asked. You are going to use it whenever you have a collision or an explosion. Now I'm going to put explosion in parentheses because for explosions, that's any time you have like one thing that then separates and becomes two things, and those two things will be moving apart. Usually that one thing had 0 momentum initially, so we're at P0 for initial momentum, and it would have had 0 kilograms times meters per second. And then afterwards, you're going to have equal and opposite momenta, the plural word for momentum, moving in other ways. Every collision and every explosion, momentum is conserved. You have elastic collisions and you have not elastic collisions or inelastic collisions. Elastic collisions, again, are things like bounce off of each other. Maybe this guy's sitting here at rest, this guy's moving along, and then afterwards, so here's you got your B4 situation, and then after, maybe as a billiard ball, this one transfers its momentum to the other one, and it sits there at rest afterwards. All the momentum has been given to this one. And then in inelastic collisions, your B4 is going to be where you've got this one rolling along, this one might be sitting still, and then after they combo on you and they kind of stick together and move together as one. And so the momentum from the original one had all the momentum to begin with, and then they both move together and you just add their masses together. So it ends up looking like this. You're going to work them in the same way every time. Conservation momentum says that your initial momentum has to equal your final momentum. So every single time you start writing like this. Momentum is a P, and initial equals momentum F for final. And then you expand these as you need to. You'll pretty much always have two objects because you're going to have two things hitting each other. And so you're going to have like the mass of object 1 times its initial velocity, and then you'll have the mass of object 2 times its initial velocity. But since those look exactly the same, we need a way to differentiate them. So I'm going to say, hey, maybe let's use letters, let's use numbers or something. Maybe object A and object B, and we'll put little A's and little B's on those guys. And then same thing here. It's kind of repetitive, but you're going to put finals. And mass A, mass B, final. Okay, so for elastic, they'll sometimes start apart and then they'll sometimes end apart. And sometimes you'll end up putting in zeros for velocity. So it expands to this long thing, but then it shortens up really fast on you. Like for example, right here. Here I have ball A and here I have ball B. Well, ball A is the only one with any initial velocity. So the initial velocity for ball B is actually going to get slashed out to a big old 0 because that's what it is doing at first, equals 0 meters per second. And then after the collision, ball A has transferred all of its momentum to ball B, so ball A ends up stopped, and it ends up VFA is a big old 0 meters per second. I don't really have space, so I'll start to squish it. There's meters per second, that squiggle. So VFA is going to go away to a 0. And it's going to simplify really fast to MA VOA plus 0, nothing there. No momentum for object B to start with. And then no momentum for object A to end with. It all gets given to the second ball. And so there's kind of an elastic general form. You can have variations on the theme. You got to stay on your feet. You got to be able to move with it. But basically, if you start here and then expand both sides and plug in zeros where they're necessary and then let it simplify out, when the dust clears, you should be able to work no matter what situation comes at you. So for the inelastic stuff, we're going to have, here's A again, here's B, and then we're going to call this, I guess, AB, because they combine, they become one thing. So we start the same way, conservation of momentum. Momentum before is equal to momentum afterwards, expand. So initially, we've got the mass of A times the velocity initial for A, plus the, I'm going to run out of space, huh? I'm just going to make this an equal sign into a velocity. Thinking on my feet. Initial velocity for B. And then I'm going to put my equal sign, and I'm going to bring this over yonder. Now, this is the trick, okay? When they combo like that, you can actually, you combo their masses. So you treat them like one thing. It's almost like two things became one. It's like marriage for these two. And the two shall be one. So now you're going to actually write MA plus MB, put it in parentheses to marry them as one object, and then they're both going to move together with one final velocity. And so you can just put VF, and you can leave it like that because it's the only final velocity. Or if you want, if you really like all these little subscripts, you could put VF AB to show it's the final velocity of the two things moving as one. And that's your general form for this. Now, what would go to 0 here? Well, initially, we just had our little B object here sitting with an initial velocity of 0 meters per second. So we go down here, we find that VOB thing, slash it out, put a 0 in for that bad boy, and you really end up shortening your equation to a little something something like this. Now just leave it VF. All right, now again, start with your PO equals PF. Expand it, and then expand it. Just watch whenever you need to combine the masses. Looking at explosions over here, explosions are really exciting, really fun. But I write explosions in parentheses because really it doesn't have to have like a big bang, a big boom. It could be an astronaut in space holding a fire extinguisher, and they were using the fire extinguisher like a little rocket, and then they're out of the fire extinguisher foam, and they still need to change their direction so they could throw the extinguisher away, and then they would be one object, and then here's the astronaut, and there's the extinguisher, and the astronaut would get a momentum in the opposite direction from the extinguisher. You've got Newton's third law talking that comes into play with that, like, you know, the force they put on the extinguisher ends up being the force the extinguisher puts back on them, and that is what creates the change in momentum for them, the impulse that they get. By the way, I got that example from the new movie Gravity. Sandra Bullock actually does that, and it saves her life in that movie there. But you start with initial momentum is going to equal final momentum. We are stating mathematically that momentum will be conserved in this event. And then what did we have initially? Well, initially they were together. If you want to use your AB stuff again, we can say, hey, initially they were AB. So we had like MA, the mass of the astronaut, plus the mass of B, maybe that's the mass of the fire extinguisher. They're together as one, and then they were moving together with an initial velocity. Their final velocity is going to be, well, their final momenta is actually going to be in opposite directions, and you're going to have to make a decision here. You're going to have to say, okay, well, one way is going to be a positive direction, another way is going to be a negative direction. That way I can show opposite directions, I can show opposite momenta. So it's going to look like this. We're going to expand this. we're going to have, here's A, here's B. So A is going to get this negative momenta, B is going to get this positive momentum, and you're going to have M, A, VF. We're on the F side, the final side. For A, it's going to have to be negative, so switch a little negative sign right in there, right there, plus M, B, V, F, B. And that's going to be your general form for explosions. Check it out. This is actually the exact opposite of inelastic collisions. Exact opposite. You know, it's two things were together, then they become separate. Two things were separate, then they come together. Put in your zeros where appropriate. Let's say they weren't moving initially, so then the initial velocity can go away. This whole side then gets multiplied by a 0. Watch your units. Your units for momentum are kilograms times meters per second. It's just the units for mass times velocity combined. And then you're going to have a negative MA VFA plus MB VFB. And you can solve for whatever you have, put in whatever you have. That's your strategy for solving conservation momentum things. Continue on to part 2 to check out hints and a practice worked out problem in the packet.